Welcome to crime scene number 3, where we join Dr. Amethyst in gathering evidence about the face-centered cubic unit cell, or FCC. It's also called cubic closest packing, or CCP, which we'll talk about when we get to the packing efficiency evidence. Now, the parameters are still going to be the same for FCC as it is for SCC and BCC, okay? And the first piece of evidence we're going to go over is the cubic arrangement. So in FCC, identical particles are going to lie at each pointer. You can see at each corner here, and lie at the center of each face, but not in the center of the cube itself. So there's actually space in between here. There's nothing in the center of the cube itself. We just have some that are lying in the center of each face. Okay? Again, the different colors are here to help you visualize. Remember, they're all the same identical spheres or identical atoms. Now, as we can see in the space filling view, those at the corners do not touch each other, so they're not touching one another, but they do touch the faces or the atoms on the center of the faces, as we see here. So we do see them touching the faces there. The second piece of evidence is going to be the coordination number, and that's always going to be based on the number of the nearest neighbors, okay? So we have the central atom here, and we have 4 neighbors above, 4 neighbors below, and 4 neighbors in the plane. So that means there are 12 neighbors surrounding the atoms, so there's a coordination number of 12. Okay, and the third piece of evidence is always going to be the atoms per unit cell. So we're still going to have our particles, our 1/8 particles at the corner, so that's going to give us 1 atom, right? And now we also have atoms at the center of the faces of our cubes itself. So we know we have 6 faces, and so if we know half of it an atom is on the face of it, then we're going to take our 1/2 times 6, which equals 3, added to the atom from our corners, and that means we're going to have 4 atoms per unit cell here. All right, folks? And we are finally back down to our final piece of evidence, which is going to be the packing efficiency. And of course, we are using our fruit being packed in the grocery store analogy. So we know that depending on how the spheres or atoms are layered, that's going to result in certain packing efficiency. The BCC was able to fill those diamond-shaped spaces for the lack that SCC had, right? But it still only had a packing efficiency of 68%. To get the highest arrangements, the closest possible packing, which is how we get the name cubic closest packing, right? From SCC as well, the first layer itself has to shift to the same smaller triangular spaces. So that means this bottom layer here, which represents the first layer, this green layer is going to represent the second layer, and this blue layer is going to represent the third layer, okay? And so what happens is we were focused on 2 layers being laid on top. And so when that second layer laid on top in BCC, we saw that it filled in the diamond-shaped holes, right? Well, what happens in FCC, or cubic closest packing, the first layer is going to shift. So instead of having diamond-shaped holes, it's now going to have triangular-shaped holes. That way, when the second layer is on top of it, you see 2 things. You see these white spaces that are here, and then you see these orange spaces that basically are showing you the first layer underneath. And so what happens is 2 things. You can either have a third layer that covers the white spaces, or have a third layer that covers the orange spaces. For us, when we're talking about face-centered cubic unit cells, or CCP, we're going to have a third layer that's going to cover these white spaces. So this white space is going to be covered, all these white spaces are going to be covered when a third layer is added. That's going to help us understand the packing efficiency of the FCC, or face-centered cubic unit cell. So if we take this and we get an expanded side view, we see that we have layer A here, B, C, and we still have a layer pattern of ABC, ABC, ABC when we have an FCC unit cell. Okay, folks? And due to this layering, the packing efficiency for FCC is going to be a whopping 74%. That means only 26% of empty space between these atoms. And this is going to make FCC the most efficiently packed cubic unit cell for atoms of the same size. That means we get to see a lot of different atoms take on this type of crystalline unit cell structure, like nickel, copper, lead, even CO2, okay, and many, many ionic compounds. We can even add more detail from the packing efficiency information. So even though, yes, it is the most efficiently packed, it can create spaces where additional atoms can fit into specific arrangements, providing locations for like other ions to occupy, which can influence like the crystal's properties or reactivity even. And so there's two types of sites or additional sites or holes, if you will, for FCC. And those two holes are going to be tetrahedral holes and octahedral holes. We also call them tetrahedral sites or octahedral sites. So a tetrahedral site or tetrahedral hole are going to be formed within gaps between four neighboring atoms. So they have a coordination number of 4. And so as you can see, this little purple area here is representing an interstitial site. So interstitial, if you see interstitial, it just means the space between, right? So it's going to be the space in between these 4 neighboring atoms here. So this one here, this one, and this. Okay? Now an octahedral, or these interstitial sites here, are going to be among 6 neighboring atoms and have a coordination number of 6. So we have this atom, this one, and then this 4 on this plane. That's going to allow this entire area to be an octahedral site or octahedral hole. So again, what happens is these little holes or sites are within the FCC packing structure, even though it is the most efficient, and that can cause extra impurities in the crystal structures, for example, or different type of crystal properties and reactivity because there could be extra ions attached to it as well. So let's go further and get details about the edge length and density of FCC. So now we're going to join Detective Emerald to again put it all together by getting down some calculations and details. So of course we're going to get the edge length from the X-ray diffraction data and apply the Pythagorean theorem and some arithmetic to find the atomic radii. So after applying the Pythagorean theorem, we see that the edge length is going to be A is equal to square root of 8r. You also can sometimes see it written as 2 square root of 2r because 2 square root of 2 and square root of 8 are equal to the same number, okay? Now, of course, if I have my edge length, I can solve for my radius. So my radius would be my edge length divided by square root of 8. And if I have my edge length or my length, then of course I can get my volume, which is going to be my edge length cubed. And with my volume, I can then get my density, which is going to be my mass divided by my volume. Now we know my mass is based on the number of atoms per unit cell. And because we're FCC, we have 4 atoms per unit cell. So we have 4 atoms per unit cell. We're going to convert atoms to moles, and then we're going to take our moles and convert it to grams by using the molar mass of whatever atom we're looking for. Once we have that mass, we can use it to help us solve for density. So if we have the variables mass and volume, we can solve for density. If we have mass and density, we can solve for volume, etc., etc. Now again, just like BCC and SCC, we're going to use all the same conversion factors. If you have to take the cube root, it's all going to be the same. So let's go ahead and do an example to crack the case for FCC and its specific parameters. All right, so to crack the case, let's do an example to connect the information. We know that, yes, some questions can be more difficult in the homework or practice exam to continue to help you add layers of information. So if you need more practice, use the textbook exercises because it can become a lot of overwhelming, especially since you have to mix and move around so many variables, okay? So the question here states, gold, which you know is going to be AU on the periodic table, has a face-centered cubic structure. So it's FCC. And it has a density of 19.3 grams per centimeter cubed. And the question wants to know, what is its atomic radius? So, oh wow, there's a lot we have to do here, right? We have to make sure we first gather information about FCC. So FCC, we know that it's going to have a coordination number of 12. The number of atoms is going to be 4. It's going to have a packing efficiency of 74%. And an edge length of the square root of 8r. So that means our radius is going to equal to edge length square root of 8. So this is what we're trying to look for, our radius. That means we have to find our edge length. So far, we're only given density. So we can write all the details we know about density. Density is equal to mass over volume. Okay, we know our volume is A cubed, and we know our mass is going to be based on the molar mass of what? Gold, and the number of cells, or number of atoms per unit cell, okay? Number of atoms per unit cell, which we know is 4 because we have FCC, okay? So as you can see, we can start asking ourselves some questions. Wait, what are we going to need in order to get our R value? Well, we're going to need A. The only way we can get A is if we know our volume here. Once we know our volume, we can get A, and then we can take the cube root of this A cubed here, to get A by itself. Once we have A by itself, we can go ahead and get our radius. So we also want to make sure that we have the correct conversion factors. So we can go ahead and write conversion factors. One of the main ones will be 1 picometer is equal to 10 to the negative 10 centimeters, okay? And the reason why I put that is because when I'm looking at my answer choices as well, I see it's all picometers. So I just want to make sure everything is connecting. And then I'm going to run and get my molar mass from the periodic table of gold, which is 196.97 grams per mole. Okay, so how do I start to basically approach this question? Well, we already have the information for FCC. We know we need the radius, and we know we need edge length, and we know it has to do with density. So we're given density, we need volume, but we also need to figure out the mass. That's something we don't know. So when you have two variables and you're like, which one do I need to figure out? You have to ask yourself, is there one that I actually can do some problem or some extra work on to get the answer? Or are they both just straight up variable? So when you look at your volume, we know this is a straight up variable. We have to get our edge length in order to be able to get our radius, right? But for our mass here, we can actually go ahead and try to approach to get our mass. So with FCC, we know the mass is going to be 4 atoms per unit cell, okay? We're going to multiply that by moles for Avogadro's number, okay? And then we're going to multiply that by the molar mass, which we know the molar mass for gold is 196.97 grams per mole. And this is going to get us grams per unit cell. So now we have our mass, we have our density, we can find our volume. So that's literally how we're going to be setting this up. Now to find volume, you can go ahead and just manipulate that variable right now. Go ahead and do that. Density is equal to mass over volume. So that means my volume is going to equal to mass over density. This is how I'm going to get A cubed. And then once I take the cube root of that, I'll be able to get A. Once I have A, I'll be able to find R. So we still have a little bit of a process, right? Let me go ahead and erase this and get us to a little bit of a setup. All right, so I have my volume. I know it's going to equal to mass over density. I already know my density is going to be 19.3 grams per centimeter cubed. That's given. I'm about to find my amount for mass. So because we're doing FCC cubic structure, which is given, we're going to have 4 atoms per unit. We're going to use Avogadro's number to convert 4 atoms to moles. Now, as you can see, I put 6.022 e to the 23. That's still the same as saying 6.022 times 10 to the 23. It's just a faster way to write it so that I'm not writing too many numbers down, okay? So I'm going to go from atoms to moles using Avogadro's number, and then I'm going to go from moles to grams using molar mass. And so when I do this, I get a very long number of 1.3083 times 10 to the negative 21 grams per unit cell. Okay, so now I have my mass. Now let's go ahead and find our volume. Now I can find my volume. So I take my 1.3083 times 10 to the negative 21 grams, which was my mass, okay, and divide it by my density, which is 19.3 grams per centimeter cubed. Once I do that, I get 6.77876 times 10 to the negative 23 centimeters cubed, which is going to represent A cubed, right? My volume. Now, if I take the cube root of the value I just got, which is the cube root of A cubed, I will get my A value. So in my calculator, I got the cube root of 6.77876 times 10 to the negative 23. And this is the answer I got. 4.0774 times 10 to the negative 8 centimeters. So now we're going to take our radius equation. Radius is equal to our edge length square root of 8 to go ahead and find radius. But as you can see, we have the unit of centimeters here. So we need to do an extra step and go from centimeters to picometers to make sure we are answering the question properly. So I have my 4.0774 times 10 to the negative 8 centimeters divided by the square root of 8. And I'm going to multiply by my conversion factor. 1 picometer is equal to 10 to the negative 10 centimeters. So the centimeters are going to cancel, and I'm left with my answer of picometers, which is 3 significant figures based on the density number that was given. So that is 144 picometers, which is going to signify letter A, okay? So this concludes our 3 cubic system crime scenes. Let's do some cross investigations to learn about other unit cells.